Anatomy review, the cardiovascular system, the heart. So let's take a quick review of the body cavities just so we can remember where the heart lies. So we have the two basic body cavities, the dorsal and the ventral, and the heart lies within the ventral cavity, specifically in the pleural cavity and the tiny cavity called the mediastinum. So you can see there are a lot of subcavities within these two major cavities. The thoracic cage is formed by the rib cage, the sternum, and the vertebral column. Its function is to protect organs of the thoracic cavity. And you can see the rib cage labeled there because there are different designations for the different pair of ribs. So we have 12 pair of ribs, and they have some different designations. So remember that the last 4 ribs are not considered our true ribs. They're false ribs, and of those 2, the last 2 are actually floating. Let's take a look at the mediastinum. So the central compartment of the thoracic cavity, and it contains heart, great vessels of the heart, esophagus, trachea, thymus, and the lymph nodes of the chest, the central chest. So these are all structures we find in the mediastinum. It lies between the right and left pleura, and near the median sagittal plane of the chest. It extends from the sternum in the front to the vertebral column in the back, and contains all of the thoracic viscera except for the lungs. Serous membranes of the thoracic cavity. So, quick review, we have different kinds of membranes in the body. Serous membranes are those membranes that are 2-layered, they're double-layered, and their function is to lubricate. We have organs that do a lot of moving, like the heart and the lungs. So those are examples of organs that are surrounded by serous membranes. The layer of that serous membrane that would line the cavity that that organ sits within is the parietal membrane, and the layer on top of the organ itself is the visceral membrane. So, in the case of the lungs, we have the parietal pleura lining the cavity of the thoracic, lining the thoracic cavity in, and we have the visceral pleura, which covers the lungs. And then in between is a small space where we find something called serous fluid. And this helps to lubricate the lungs as they expand and deflate during breathing, and also helps to create a pressure that keeps the lungs inflated. In the heart, we have the same kind of membrane. In this case, it's called pericardium. The pericardium actually, it also, in addition to being a serous membrane, contains a fibrous layer. So the pericardium is a double-walled sac that protects the heart, and its outer fibrous layer is really protective to the heart, and then its inner serous layer is that serous membrane that I'm talking about. So in the case of the heart, we have parietal pericardium lining the mediastinum and visceral pericardium covering the heart. So let's look at that pericardium a little closer. Again, double-walled sac surrounding the heart, functions to protect the heart. It anchors it to surrounding structures and prevents it from overfilling. The parietal layer is just internal to the fibrous part of the pericardium, and the visceral layer lies directly on top of the heart. We also call that the epicardium. Together, these two layers form a continuous, uninterrupted membrane. The pericardial cavity lies between and contains pericardial fluid. Here's a better picture of the pericardium so you can see if we were to remove a heart, then that membrane that you see there in that diagram is the pericardium. And then if you were to take a closer look right on top of the heart, you'd see the epicardium. Let's talk about the anatomy of the heart. So again, the heart is in the mediastinum. It's a hollow muscular pump that pumps blood through the blood vessels by repeated rhythmic contractions. The term cardiac, if you remember from medical terminology, as in cardiology, means related to the heart. It's composed of cardiac muscle. It's involuntary, and we only find cardiac muscle in the heart. The heart and its great vessels are all labeled there in the diagram. We've covered this a few times already, but again, the heart is located in the mediastinum, and you can actually see exactly where the heart lies in this cavity in the diagram, just a little bit to the left, with the apex of the heart being a little inferior and left around ribs 4 and 5, and the base of the heart pointing in a superior and direction off to the right. So we could say that it has an oblique orientation from the second rib to the fifth intercostal space. It's deep to the sternum, anterior to the vertebral column, and rests on the superior surface of the diaphragm. Let's take a peek at the heart walls. If we were to cut the heart and just look at the wall, we'd see that very thick myocardium. Since the heart is mostly muscle, there are really three layers to the heart wall. The epicardium is the outer layer of heart tissue. Again, we talked about that as visceral pericardium. Deep to that is the myocardium. This is cardiac muscle tissue. And then lining all of the chambers is endocardium. It is an epithelial tissue that lines the chambers of the heart. Heart chambers. So there are 4 heart chambers, 2 upper and 2 lower. The 2 upper are called atria, and the 2 lower are called ventricles. The top chambers are designed to receive blood from the veins of the body, and the lower chambers are designed to receive blood from the atria, and they also will pump blood away from the heart. So we consider the top 2 chambers receiving chambers, and the lower 2 chambers, the 2 ventricles, the pumping chambers. The right atrium, and we're going to kind of go in, we can just jump in and go in a sequence here of blood flow. So the right atrium would receive deoxygenated blood from the superior and inferior vena cava, and it will pump blood through the right atrioventricular valve, also called the tricuspid valve, into the right ventricle. From the right ventricle, which receives blood from the right atrium, blood will be pumped. It's deoxygenated at this point through the pulmonary semilunar valve into the pulmonary trunk, through the pulmonary arteries, because remember, arteries carry blood away from the heart, and to the lungs for oxygenation. There are chordae tendineae that anchor the valve flaps to the chamber wall. And just side note, this is the only place in the body where an artery is carrying deoxygenated blood. Left atrium. Again, atrium is a receiving chamber. The left atrium is going to receive oxygenated blood from the pulmonary veins, and then will pump blood into the left ventricle through the left atrioventricular valve or bicuspid valve. Once the left ventricle receives blood from the left atrium, it will then start to contract, and it will pump blood out of the aortic semilunar valve, through the aorta, and out to the body. It has a thicker wall, a thicker muscular wall, so more myocardium than the right ventricle, because it has to pump blood under a high pressure, and the aorta is considered a high pressure valve. And then from the aorta, blood is going to travel, oxygenated blood will travel to all of the other arteries in the body and oxygenate our tissues. All right, let's take a step back and look at those heart valves. We just talked about how blood is pumped through valves. The main function of a valve is to prevent backflow of blood, promoting unidirectional flow. So as blood is moving through our cardiovascular system and our vessels, it is going to go in one direction only. So valves are positioned in the heart to help prevent backflow so that blood can pump through the heart in one direction, and also to help maintain the pressure needed for the heart to pump blood over long distances through high pressure valves. There are 4 heart valves. The 2 atrioventricular valves function to prevent backflow from the ventricles into the atria. So once blood passes through them, then back pressure will shut those valves and no blood will go back into the atria. It will stay in the ventricles, where then it will be pumped through the semilunar valves into the vessels that carry blood away from the heart. And again, once the ventricles build up enough pressure to pump, they will pump blood through those semilunar valves, and then blood will close. Backflow of blood will close those valves to keep blood from coming back into the heart. What you hear when you use your stethoscope, the lub-dub that you're hearing, are those heart valves shutting. So heart valves closing, slamming shut against back pressure of blood, gives us heart sounds. When we have irregular heart sounds, we call those murmurs. So here's another image of the heart. You can pause, take a look at it, or just look at it on the PowerPoint. This is a heart cut in half so that you can see really the contrast between the myocardium of the left ventricle and the myocardium of the right ventricle. Blood circulation. So again, it's a side-by-side pump where blood is moving top to bottom from atria to ventricles. It's a side-by-side pump because we consider the right side to be pulmonary, the pulmonary circuit. So these vessels, this part of the heart and the vessels are carrying blood to and from the lungs. Short duration, low pressure circuit. Left side is the systemic circuit. These are vessels that carry blood to and from all the body tissues. There's much more resistance in these vessels, and the left, which means the left ventricle has a thicker myocardium so that it can pump blood against that greater pressure. Do note that equal volumes of blood are pumped to the pulmonary and systemic circuits. And here's a picture of those two circuits divided and color-coded so that you can see the deoxygenated blood versus the oxygenated blood. And this is a great slide just to review the pathway of blood through the heart. Again, it's a closed circuit, so we don't start anywhere, but if you want to jump in anywhere along the pathway, then you can just move in sequence following the arrows that I have listed here. Will show you the pathway of blood through the heart. It's great practice. Coronary circulation. So the heart being tissue, the heart being a living tissue and a muscle, it's going to need its own blood. So it has a coronary circulation. So this functions to supply blood to the heart muscle. Because it is imperative that the heart muscle get blood, if we ever had a block in a vessel, that would be the end of it, right? So we have a lot of anastomoses or junctions or branches in the heart's coronary circulation so that there's always an alternative pathway for blood to flow when it gets to heart muscle. So you can see that when major arteries are blocked or when arteries that precede these anastomoses are blocked, that can cause death of certain parts of the heart muscle. We call that a myocardial infarction. So lots of collateral routes are there. It's not a foolproof system, but it's definitely a great system. People can go for a really long time with a partial or even sometimes a complete blockage because of these anastomoses. In the arteries of the coronary circulation include the right and left coronary artery. They lie in the atrioventricular groove, the marginal artery, the circumflex, the anterior interventricular arteries, and then in veins, we have the small cardiac vein, the anterior cardiac vein, and great cardiac veins. And then here are the diagrams that show the coronary arteries and the coronary veins. Moving on to the electrical events of the heart. So the heart being a muscle, it pumps in rhythm. So one of the ways that this heart pumps in rhythm is that it has its own nervous system. So the intrinsic cardiac conduction system is listed here. An impulse to the SA node or sinoatrial node, which you call the pacemaker of the heart, will then send a signal to the AV node, which then sends signals to the AV bundle, which then sends signals to the right and left bundle branches, and then up to the Purkinje fibers. And you can see heart contraction occurring from top to bottom like that. So the two atria contract at the same time, and the two ventricles contract at the same time in response to the electrical events created by this intrinsic cardiac conduction system. Some homeostatic imbalances. Arrhythmias or irregular heart rhythms. Sometimes people can live a long time or their whole lives with arrhythmias. Fibrillation, on the other hand, is a different situation. This is where we have rapid, irregular contractions. This makes the heart useless for pumping blood, which then, of course, would lead to loss of circulation and brain death. So fibrillation is what is normally happening when a person's having a heart attack, which is why we have those AEDs, and they can defibrillate the heart. So they basically stop the heart for, a brief second, giving it a chance to regain its rhythm. A defective SA node can lead to an ectopic focus. In this case, people usually get a pacemaker put in. In a defective AV node can result in partial total heart block, where few or no impulses from the SA node are actually reaching the ventricle. So again, very serious issues, most of the time treated with an artificial pacemaker. And that concludes our presentation.